All right, what we just learned about the integration. Okay, so that's tell you the number of protons giving rise to each signal. The last information in the proton NMR is spin multiplicity. Okay, or splitting patterns. Some people say that. So spin multiplicity indicates the number of non-equivalent neighboring protons. We're going to focus on the word neighboring protons. Okay, what does neighbor mean? Make sure that's clear. I mean, some students somehow get confused with the word neighbor. All right. Let's say if I have two houses. Okay, let's say on the left side you live with your, let's say, your parents, your cousin. Do you call your parents or your cousin neighbor? No, you live in the same house. That's not a neighbor. Okay, they're not neighbors. But if you have your friends, maybe relative on the next door, on the house next door, those are neighbors. All right. So this we can compare this to refer back to protons on each carbon. The carbon is the house. Okay, so we have red protons on one house, on one carbon, and the blue protons on the other carbon. All right. So I'm going to ask you this: how many neighbors do the red protons have? How many neighbors do the red protons have? Three neighbors. That's three blue protons. What about the blue protons? How many neighbors do they have? Well, only two, because you count this. You don't count this neighbor. These are the same house. All right. All right. Here's what happened. So the orange proton have three neighbors. So right here, three neighbors, and the red got two neighbors right here. All right. How many neighbors do the blue protons have? Zero. Good. I said blue right here. This is red. This is blue. Okay. All right. Here's what happened. The shape of the signal of the orange proton, three neighbors show up, four peaks. We call quartet. All right. The four peaks actually come from by itself, one, and then one neighbor, two neighbors, three neighbors. That's why you see four peaks. Try one more time. If you don't get this, one more time. The red protons. Okay. How many peaks will it show? Well, by itself, that's 1, 2, and 3. You see a triplet. By itself, 1, 2, and 3. Some people confuse, hey, but there are three of the red proton. Well, these three red proton have the same chemical shift. They add up. You don't count like 1, 2, and 3 right here. You count the neighbors, right? By itself, 1 peak, and then 2 neighbors, 2 more peaks, so 3 peaks total. The orange proton by itself, 1 peak. By itself, 1 peak, and the three neighbors, 3 more peaks, 4 peaks total. What's the shape? How many peaks do with the blue proton show? No neighbors, just by itself, 1 peak, just by itself. And guess what? Look at the real spectrum. Yeah, quartet, a triplet right there, triplet, right, and a singlet right there, just like that, right? Now go back right here. So you have seen this before in the integration, but this is a common spin multiplicity by substituent. All right. In ethyl, these 2 red protons right here have 3 neighbors on the right side right here. Got 3 neighbors, so this guy gonna be quartet. Look like that. And the CH3 outside got 2 neighbors, a triplet. If you see a quartet and triplet, it's kind of tell you, hey, you got an ethyl group. You have to recognize that. Okay, it's gonna take some time to practice to be familiar with this spin multiplicity. All right. Now in isopropyl, the proton in the middle got, was it 1, 2, 3, 4, 5, 6 proton outside, so 7 peaks. You're gonna see a septet, right? But most of the time, septet is really difficult to see, so we just call them multiplet. Right, but if you can make a nice septet, you can actually see septet there. So 1, 2, 3, 4, 5. There's little one, 6, 7 on the side, really small. That's a septet. Now the green proton outside though got 1 neighbor, a doublet. A septet and a doublet, it tells you got an isopropyl. Right? I think I missed L right here. PYL, isopropyl. Okay. All right, one more. We have third butyl. So what is spin multiplicity of that proton in the middle? It's a trick question. There's no proton in there. There's no proton, no signal. Okay, there's no signal there. The outside though, the green proton, do they have neighbor? No proton here, so no neighbor. Singlet. They're just a singlet. Okay, you have to look at the integration, 9 hydrogen integration. All right. Now move on to the benzene ring down here. So the red proton. So what's the spin multiplicity? 1 neighbor, a doublet. The green proton got how many neighbors? 1 and 2. So 2 neighbors, you get a triplet. The blue proton here, you got two neighbor, 1 and 2. So we got a triplet, doublet, triplet. Take a look. We have doublet right here, a triplet and a triplet. Really close in here. Sometimes we just call this multiplet if you can actually differentiate them. Okay. Last one, dipara substitute benzene. So we got two type of proton. Each one of them got one neighbor. So the red one got one neighbor, a doublet. The green one got one neighbor, also a doublet. So double doublet tells you there's a para disubstitute benzene. All right. Now, a little bit of shape, not as important, but a little bit about the shape of the spin multiplicity. So we have a singlet, right? Doublet, so like two peaks, really close in intensity. A triplet, so 1 to 2 to 1 ratio. All right. We got a quart 1 to 1, 2 to 2 to 1. A quartet 1 to 3 to 1 ratio. A quintet, that's 5, 1, 4, 6, and 1. You don't need to know this number, right? But there's something that controls this ratio, but we not get to that, right? But basically, when you draw, we're gonna have you sketch. When you draw this out, they are actually symmetrical. Try to make them symmetrical. A triplet, a quartet, a quintet, and a septet. Make them symmetrical, right? So many times you're gonna see multiplet, but multiplet you can't really tell what's in there. All right. All right, so we're going to talk about a couple exception about on spin multiplicity.